When you store a bearer token directly in a browser's local storage, you expose it to every injected script. If a single third-party dependency in your application is compromised, attackers can execute a cross-site scripting attack. They silently read the local storage and exfiltrate your users' active access tokens, granting themselves unauthorized access to your systems. The OAuth 2.1 framework addresses this specific threat vector by deprecating the legacy implicit grant flow. Access tokens are no longer returned directly to the user agent via redirects. We cannot treat the browser as a secure environment. Securing modern enterprise architectures requires engineering a zero-trust identity and access management system from the ground up. To build this, we must secure the token across 3 distinct phases of its lifecycle: acquisition, transit, and verification and revocation. We begin our blueprint with a blank canvas, mapping only the client application and the authorization server. Our first step is securing how the client requests and acquires the token, ensuring the handshake cannot be intercepted by a man-in-the-middle attack. A single cryptographic flaw during this initial acquisition phase compromises the entire downstream architecture. OAuth 2.1 mandates the authorization code flow as the baseline protocol for all clients. The core security control of this phase is Proof Key for Code Exchange, or PKCE. First, the client generates a random string, hashes it, and sends the hash with the authorization request. During the token exchange, the client proves its identity by presenting the raw string. The server hashes this string, confirming it matches the challenge before releasing tokens. To prevent attackers from routing authorization codes to malicious domains, OAuth 2.1 also enforces exact character-by-character string matching for all redirect URIs. While PKCE secures the token during network transit, the token now faces its greatest threat, resting statefully inside the client environment. The primary defense against JavaScript-based supply chain attacks is the backend for frontend, or BFF, architectural pattern. A BFF acts as a confidential client. It handles the token exchange and keeps all OAuth tokens strictly quarantined on the backend servers, away from the browser. The BFF establishes a secure connection with the browser by issuing a restricted, encrypted session cookie, configured with HTTP only and same site equals strict flags. The browser makes API requests using this cookie. The BFF intercepts the request, maps the cookie to the cached token, and proxies the authenticated request downstream to resource servers. This pattern maximizes security by isolating the browser, but mandatory request proxying adds severe network latency and heavy processing overhead that creates bottlenecks for high-traffic systems. For systems requiring direct, low-latency client-to-API communication, the alternative is demonstrating proof of possession, or DPoP. DPoP generates a key pair locally, binding the token to that hardware context. The server embeds the public key thumbprint directly into the token payload. For every API call, the client uses its private key to sign a short-lived proof document. DPoP ensures that even if an access token is stolen via XSS, it is mathematically inert without access to the client's localized private key. Shifting our focus down to the internal architecture, we must secure how back-end microservices handle thousands of requests per second. Resource servers cannot make a synchronous network callback to the authorization server to validate every single token without creating a catastrophic systemic bottleneck. Instead, enterprise systems utilize JSON Web Key Sets, or JWKs, for offline, stateless cryptographic validation. The resource server fetches and caches a public JWKs document. It matches the key ID in the token header against its cache to verify the signature. Keys rotate periodically. Overlapping new keys with passive old ones in the JWKs allows seamless validation during transitions. JWKs enables high concurrency horizontal scaling by eliminating central validation bottlenecks, but its stateless design cannot trigger an immediate revocation before a token naturally expires. Immediate token revocation is required to kill compromised sessions or enforce administrative bans. To achieve this, we deploy an in-memory Redis database acting as a high-speed block list. It stores the unique IDs of revoked tokens until their natural expiration time. But querying a central Redis cluster for every single API request would eventually saturate the network bandwidth. We resolve this by deploying a Bloom filter at the API gateway, acting as a high-speed gatekeeper. A negative result guarantees the token is not revoked. A positive result indicates a probable match, triggering a fallback exact query to Redis. Layering Bloom filters over an in-memory cache resolves the stateless versus stateful paradox. It allows for high-speed local validation while maintaining a path for immediate global revocation. Viewing the macro architecture, the system must dynamically respond to identity changes originating from external corporate directories. We integrate external identity providers using SCIM 2.0, a standardized protocol for automated user provisioning. SCIM deprovisions users through a soft delete pattern. This deactivates the user identity while preserving the referential integrity of your relational database records. When an account is deprovisioned, the system triggers a backchannel logout. It fans out asynchronous requests containing a cryptographic logout token to every dependent microservice. These microservices intercept the logout token, verify its issuer, and immediately purge their local session stores. By stacking OAuth 2.1 flows, DPoP or BFF boundaries, and SCIM-driven governance, engineers can architect a hardened identity ecosystem capable of neutralizing the most common classes of session-based attacks.